Before we jump into a couple of examples, I actually wanted to look at this applet a little bit more because it shows some kind of interesting principles that help us understand what's going on with these rays. Unfortunately, you can only do converging lenses with this, which is too bad. Otherwise, I would like this applet best, but you can't do mirrors or diverging lenses. So anyway, this is the type of diagram we typically draw, right, with these three lenses here. But actually, there's a whole lot more rays than that. So we have a picture like this, where there's rays going out in all directions from a single point, and it's those that happen to be passing through the lens that get focused at the location of our image. And the other thing I want to point out is there's not a bunch of rays coming only from that single point. There's a bunch of rays coming from every single point on our object. So all these rays here, they all go through the lens and they get focused at the corresponding location on the image. So this is what is kind of a more close representation of reality. The other thing I wanted to show you with this, let's jump back here to our old picture. What happens if we change the size of this lens? Well, that doesn't actually change where our image is located. If you look closely, it just changes how bright or how dim that image is, because it's collecting more light, but it still gets focused to the same point. And this is why we need really large lenses on telescopes if we want to see dim, distant objects like faint galaxies far, far away. Okay, now jumping back to solving some problems. So, sunlight focused at a point 16.5 centimeters behind a lens. We want to know what kind of lens that must be and what is its power in diopters. So I've got sunlight coming in, which means parallel rays. Okay, and if it gets focused behind the lens, that means on the other side of the lens. The only possibility for that is a converging lens. We don't know exactly what shape it is, but sorry, my rays kind of start bending before they hit. But anyway, you'll get something along those lines. Beautiful picture there. Okay, so this, what kind of lens is it? It's a converging lens. Because diverging lenses won't focus anything on this side, they will spread the rays out. They will appear to have focused them over here. They don't actually focus anything, right? Okay, converging lens. The other thing we want is the power in diopters. So to get power, that's related to our focal length. So really what we want to look for first is focal length. So we use our new equation, the lens equation. 1 over image distance, 1 over object distance equals 1 over the focal length. Now this 1 over the focal length thing is the power in diopters. So we can actually just set this equal to the power if we want, or you can solve for the focal length first and then invert it, but you can solve for the power directly this way. The image distance is sunlight, so that image is out, sorry, not the, let me come back to the image distance actually. Well, the image distance is given, 16.5. We do need to be careful since we want the power in diopters. We need to convert that to meters, so 0.165 meters. Okay, this is what I tried to start with. The object distance is out at infinity, so this guy goes to 0, and we can just find the power that way. So 1 over 0.615 is going to give us a power of 6.06 diopters. There we go. And because it was on this side of the image was on this side of the lens, we had to make sure and have this positive. Remember, we switched that before. If our images were on this side, we made those negative. But now with lenses, they're positive because that allows us to keep our convention for the signs on real and virtual images is why we do that. Okay, well, one more example. We have a 3.5 diopter lens, 12 centimeters from a little object. What is the position, type, and height of the image? Actually, we're not going to do height. We're not going to worry about that. We just want to know the position and the type of the image. Guess I shouldn't have crossed out of the image, but anyway. So to start with, we'll find the position of the image, and that is going to allow us to figure out what type of image it is. So again, 1 over dO plus 1 over dI. Doesn't really matter which one you put first, right? Equals 1 over F, or if we want, we can just call this, since they give us diopters again, rather than putting 1 over f, we can go ahead and put power over here. So the object distance is given, that's 12 centimeters. Again, we got to be careful, since this is in diopters, we need this in meters, so 0.12 meters. Image distance, that's what we're trying to find. That's going to tell us, that's what we mean by the position of the image. So we're solving for 1 over di. We have that set equal to the power of our lens. So if we do a bit of algebra, we're going to have this, which is going to end up being 1 over di equals negative 4.8333. And then we invert that, and we get an image distance of negative 0.207. That seems like it's small, but that's because it's in meters, so that's negative 20.7 centimeters if we want. Switch it back to centimeters. So there's our location. This negative sign tells me, let's have an arrow here for our image, and I'm just going to draw our lens as a line because we haven't talked about whether it's converging or diverging yet. And this was 12 centimeters here, right? And because we get this negative sign on our image distance, that means it's on the same side of our lens, here's our lens, as the object. So it is back over here somewhere. We didn't really look at the size, and it is going to be virtual. That's why I drew it dotted like this. And this here is going to be our 20.7 distance out here. So the only way we can get this is with a diverging lens, and the negative sign, just like before, if we ever had a negative image distance for a mirror, that tells us this is a virtual image. Whenever we have virtual images, they are also upright. So those two things are determined by the sign on our image distance right there. Alright. If we wanted to find the height, we would just plug into hi-ho equals dido, and away we would go. Alright, catch you next time.